Today we are diving into a really fascinating puzzle, one that's kind of hiding in plain sight inside one of the most basic rules in all of calculus. It's a story about a rule that works almost all the time, except for one very specific, very dramatic case. So, just think about that for a second. How can a single math rule, one that works for nearly infinite set of problems, have just one single point of failure? What is this one weird exception, and more importantly, why does it break everything? That's the mystery we're going to crack today. To really get why it fails, we first have to meet our hero, the power rule for integration. This is the absolute go-to, the reliable workhorse for pretty much any function that looks like x raised to some power. Now the beauty of this rule is just how elegant and simple it is. You just take your exponent, n, you add 1 to it, and then you divide the whole thing by that new number. Simple, right? It's incredibly effective, and it works for this huge universe of functions, everything from x squared all the way up to x to the power of a million. It is, without a doubt, the heavy lifter of basic calculus. But, every hero has a weakness, a kryptonite. And now we're going to zoom in on that one exact spot where this unbelievably reliable rule just hits a brick wall and completely fails. And here it is. This is the culprit. The function f of x equals 1 over x. Or if we're speaking in exponents, that's x to the power of -1. This one, specific value, n equals -1, this is where all the chaos begins. So let's actually walk through it. Let's see what happens when we try to force our trusty power rule to work here. We start with x to the power of -1. We follow the steps, right? Add 1 to the exponent. Okay, -1 plus 1, that's 0. So far, so good. But the very last step is to divide by that new exponent, and we find ourselves trying to divide by 0. And boom, it's undefined. The whole calculation just implodes. You cannot divide by 0. It's a fundamental no-go in math. Our hero, the power rule, has totally failed us, and it leaves this massive gaping hole in our calculus toolkit. So, what do we do? Well, here's the twist. It turns out the solution doesn't come from some clever patch to the power rule. Nope. It comes from a totally different and honestly pretty unexpected corner of mathematics. The integral of 1 over x? It isn't another power function at all. It's the natural logarithm of the absolute value of x. It's in a completely different family of functions. It's like we were looking for an apple, but the answer was an orange, and it turns out the orange was exactly what we needed all along. And this is where you see that beautiful symmetry of calculus that just makes it all click. The reason this works is because integration and differentiation are just opposites. They undo each other. If you take the derivative of the natural log of x, you get exactly 1 over x. So when we integrate 1 over x, we're just running the process backward to find where it came from, the natural log. It's a perfect, elegant fix. Okay, so now that we've solved the big mystery, let's put our special case side by side with one of its close relatives to really let this difference sink in. This is where we see the two paths really diverge. Let's check out the function 1 over x squared. I mean, it looks almost the same as 1 over x, right? And as an exponent, it's x to the -2. It's just one single number away from our problem case. But oh man, that one little number makes all the difference in the world. Just watch how smoothly the power rule handles this one. You start with x to the -2, add 1 to the exponent, you get -1. Then divide by that new exponent, -1. See? No dividing by 0, no drama, no problems at all. It simplifies cleanly to -1 over x, a totally normal rational function. Seeing it laid out like this makes it crystal clear, doesn't it? When that exponent is -1, the answer is logarithmic. When it's -2 or -3 or literally anything else, the answer is a rational function. A teeny tiny change in the input leads to this massive change in the output, putting the solutions in completely different mathematical universes. So let's just boil this all down into a super practical tool you can actually use. Here's the simple checklist. Anytime you see an x in the denominator of something you need to integrate, just pause and ask one question. Is that x raised to the power of exactly 1? If the answer is yes, your brain should immediately jump to natural log. If the answer is no, you're totally safe to use the good old power rule. Now you might be thinking this is just a neat little math trick, but this distinction isn't just for a final exam. It actually describes some really fundamental differences in how our physical universe actually works. And this is where it all connects back to the real world. In chemistry, when you're calculating the work done by a gas as it expands, the formula involves 1 over the volume. You integrate that, and the result is logarithmic. But then, hop over to physics. When you calculate the potential energy from gravity, the force is related to 1 over the radius squared. You integrate that, and you get a completely different kind of answer, a rational one. The universe itself actually follows these two distinct mathematical paths. Which really leaves us with this final thought. Mathematics is the language that the universe is written in. And knowing the difference between the integral of 1 over x and 1 over x squared, that's not just about passing a class. It's about learning the specific grammar you need to correctly describe everything from an expanding gas to the pull of gravity between planets. It's how we learn to speak that language correctly.